In November 2010, a team of astrophysicists staring at data from NASA's Fermi Gamma-ray Space Telescope noticed something that shouldn't exist. Two colossal structures, invisible to human eyes, stretching 50,000 light-years from end to end, towering above and below our galaxy like the wings of some cosmic butterfly. They had been there for millions of years. No one had ever seen them before. And to this day, we still don't fully understand what created them. This is the story of one of the most mysterious discoveries in modern astronomy. This is the story of the Fermi Bubbles. Our Milky Way galaxy is a relatively quiet place these days. A spiral disk of 400 billion stars, gently rotating through the cosmos, home to countless planets, moons, asteroids, and at least one species curious enough to look up at the night sky and wonder what's out there. From our vantage point on Earth, about 26,000 light-years from the galactic center, the Milky Way appears as a faint band of light stretching across the darkness. It seems peaceful, eternal, unchanging, but appearances can be deceiving. Hidden from our visible light telescopes, detectable only through specialized instruments that can see forms of radiation invisible to human eyes, there exists a structure so vast, so energetic, and so violent that it challenges our understanding of galactic evolution. Two bubbles of superheated gas and high-energy particles, each one roughly the size of our galaxy's visible disk, inflated above and below the plane of the Milky Way like balloons attached to the galactic center. They glow not with visible light, but with gamma rays, the most energetic form of electromagnetic radiation in the universe. To put their scale in perspective, if you could somehow travel at the speed of light, the fastest speed possible in our universe, roughly 300,000 kilometers per second, it would take you 25,000 years to travel from the center of the Milky Way to the edge of just one of these bubbles. The light we see from the most distant stars in our galaxy has been traveling for tens of thousands of years. And yet these structures dwarf even those distances. The story of their discovery begins not with the bubbles themselves, but with a telescope that was designed to see the invisible. The Fermi Gamma-ray Space Telescope, named after the Italian physicist Enrico Fermi, was launched by NASA on June 11, 2008. Its primary mission was to survey the high-energy sky, mapping the sources of gamma radiation throughout the universe. Gamma rays are produced by the most extreme phenomena in existence: supernova explosions, pulsars spinning hundreds of times per second, matter falling into black holes, and collisions between particles accelerated to nearly the speed of light. On Earth, we're protected from cosmic gamma rays by our atmosphere, which absorbs this deadly radiation before it can reach the surface. But from space, the Fermi telescope had an unobstructed view of the gamma-ray universe. What scientists expected to find was a relatively uniform glow of gamma rays from the disk of the Milky Way, produced by cosmic rays, high-energy particles, colliding with interstellar gas. This diffuse emission had been observed by earlier gamma-ray telescopes and was well understood. The galactic plane should light up in gamma rays, while the regions above and below the disk should be relatively dark and quiet. That's not what they found. Douglas Finkbeiner, an astronomer at the Harvard-Smithsonian Center for Astrophysics, had been studying the gamma-ray sky for years. Along with his colleagues Meng Su and Tracy Slatier, he was analyzing data from the first 2 years of Fermi's observations. To reveal faint structures, they had to carefully subtract all the known sources of gamma-ray emission: the expected glow from cosmic ray interactions, the point sources from pulsars and distant galaxies, the instrumental noise. When they removed everything they understood, something remarkable remained. Two enormous lobes, symmetric about the galactic center, extending perpendicular to the plane of the Milky Way. They were sharp-edged, well-defined, and radiating intense gamma-ray emission. They looked almost artificial in their geometric perfection. Two bubbles, each roughly half the diameter of the entire galaxy, inflated like cosmic soap bubbles from whatever lurked at the center of the Milky Way. The team double-checked their work. They verified their data processing. They consulted with colleagues. The bubbles were real. Their paper, published in the Astrophysical Journal in 2010, sent shockwaves through the astronomical community. Here was a structure on almost incomprehensible scale that had somehow escaped detection for all of human history. A structure that must have been created by an event of extraordinary violence. A structure that held clues to the turbulent past of our supposedly quiet galaxy. But to understand why the Fermi bubbles are so significant, we need to take a step back and consider what we know about the center of the Milky Way. The heart of our galaxy is a crowded, chaotic place. Stars are packed together 1,000,000 times more densely than in our neighborhood. Massive stellar remnants, neutron stars, and stellar mass black holes orbit in complex trajectories. Streams of hot gas swirl through magnetic field lines. And at the very center, anchoring the entire galaxy's rotation, sits a supermassive black hole. We call it Sagittarius A star, named for its position in the constellation Sagittarius. It contains approximately 4 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. Its event horizon, the boundary beyond which nothing, not even light, can escape, is about 12 million kilometers across. In cosmic terms, this is almost unimaginably small, but its gravitational influence extends across the entire galaxy. Supermassive black holes are found at the centers of nearly all large galaxies. They are cosmic anchors, gravitational wells so deep that they shape the evolution of their host galaxies over billions of years. But they are not passive objects. When matter falls toward a supermassive black hole, it doesn't simply disappear. Instead, it forms a swirling disk of superheated material called an accretion disk. Friction within this disk heats the gas to millions of degrees, causing it to radiate intensely across the electromagnetic spectrum. In some cases, magnetic field lines threading through the disk can launch powerful jets of material perpendicular to the disk, accelerating particles to nearly the speed of light and shooting them thousands of light years into intergalactic space. When a supermassive black hole is actively feeding, consuming large amounts of gas and dust, we call an active galactic nucleus, or AGN. The most powerful AGN, found in distant galaxies, are called quasars. They can outshine their entire host galaxy by 100 times, visible across billions of light years of space. The jets from quasars can extend for millions of light years, carving cavities in the hot gas that fills galaxy clusters and influencing the formation of stars in neighboring galaxies. Sagittarius A star is not currently active. It consumes very little material, radiating only a tiny fraction of what it could if it had a steady fuel supply. It's a sleeping giant, barely sipping at the occasional asteroids and gas clouds that wander too close. But this wasn't always the case. The evidence suggests that our galaxy's central black hole was much more active in the past. X-ray observations have revealed shells and bubbles of hot gas surrounding the galactic center, suggesting past outbursts. Studies of the molecular gas near Sagittarius A star show evidence of violent disruptions within the last few million years. And then there are the Fermi bubbles themselves, perhaps the most dramatic evidence that our galaxy's core once roared with energy. The leading hypothesis for the origin of the Fermi bubbles is that they were inflated by a period of intense activity from Sagittarius A star. Millions of years ago, according to this theory, a large amount of material fell toward the central black hole. Perhaps it was a giant molecular cloud containing enough gas to form millions of stars. Perhaps it was the disrupted remnants of a smaller galaxy, cannibalized by the Milky Way and funneled toward its center. Whatever the source, the sudden influx of fuel woke the sleeping giant. As the accretion rate increased, the region around Sagittarius A star would have brightened dramatically. Jets of material might have erupted from the poles of the accretion disk, carrying energy and particles outward at relativistic speeds. This jet-driven wind would have plowed into the gas above and below the galactic plane, sweeping it up like a snowplow, clearing a road. Over millions of years, the jets would have inflated two enormous cavities in the galactic halo, their edges defined by shock waves where the fast-moving wind material collides with the surrounding medium. The gamma-ray emission we observe today would come from this shock boundary. When high-energy particles, cosmic rays accelerated by the shock, collide with photons or gas atoms, they produce gamma rays. The bubbles are essentially vast particle accelerators, converting the energy of the past outburst into a diffuse glow of the highest energy light in the universe. But this explanation, compelling as it is, raises as many questions as it answers. If the Fermi bubbles were created by jets from Sagittarius A star, the outburst must have been relatively recent in cosmic terms, within the last 10 to 15 million years. Otherwise, the sharp edges of the bubbles would have diffused and faded. This timeline is consistent with other evidence of recent activity near the galactic center, but it also means that our galaxy might have looked very different in the not-so-distant past. If an observer in a nearby galaxy had turned their telescopes toward the Milky Way 10 million years ago, they might have seen our galaxy blazing with the light of an active nucleus. We wouldn't have been the quiet spiral we are today. We would have been a cosmic beacon. There's another possibility, though. Some researchers have proposed that the Fermi bubbles weren't created by the central black hole at all, but by an intense burst of star formation near the galactic center. The inner few hundred light years of the Milky Way contain some of the most massive and short-lived stars in the galaxy. These stars burn through their nuclear fuel in just a few million years before exploding as supernovae. A concentrated burst of star formation, triggered perhaps by the same infalling gas cloud that might have fed the black hole, could have produced thousands of supernovae in a relatively short time. The combined energy of these explosions, what astronomers call a starburst-driven wind, could have blown material out of the galactic plane, creating structures similar to what we observe. Starburst-driven winds are observed in other galaxies. The nearby starburst galaxy M82, for example, shows dramatic plumes of hot gas extending from its disk, driven by the collective fury of millions of young, massive stars. These plumes are visible in X-rays and an optical light filtered to reveal hydrogen emission. They demonstrate that stellar feedback, the energy returned to the galaxy by star formation, can rival even the power of an active galactic nucleus. Distinguishing between these two scenarios, black hole activity versus starburst wind, has been a major focus of research on the Fermi bubbles. The truth is, both mechanisms might have contributed. The galactic center is complex enough that a single explanation might be insufficient. Perhaps Sagittarius A star erupted with jets while simultaneously a burst of star formation was occurring nearby. The Fermi bubbles might be the product of both phenomena working together, their energies combining to inflate the largest coherent structures in our galaxy. Let's consider the evidence in more detail. The gamma-ray spectrum of the Fermi bubbles provides clues to the processes generating the emission. Gamma rays can be produced through several mechanisms. One is inverse Compton scattering, where high-energy electrons collide with low-energy photons, such as those from the cosmic microwave background or starlight, and boost them to gamma-ray energies. Another is hadronic interactions, where cosmic ray protons collide with atomic nuclei in the interstellar medium, producing particles called pions that quickly decay into gamma rays. Early observations suggested that the gamma-ray spectrum of the Fermi bubbles is relatively hard, meaning it contains a higher proportion of high-energy gamma rays than would be expected from some models. This hardness was initially interpreted as evidence for an electron population responsible for the emission through inverse Compton scattering. More recent analyses, with better data and more sophisticated modeling, have complicated this picture. There's still debate about whether the gamma rays come primarily from electrons or protons, or some combination of both. The sharp edges of the bubbles are another important clue. If you inflate a balloon in still air, it maintains a relatively well-defined boundary. But if there are strong winds or turbulence, the edges become ragged and indistinct. The fact that the Fermi bubbles have such clear boundaries suggests that they are expanding into a relatively calm medium, and that the shock front at their edges is still active and well-defined. This implies that whatever created the bubbles is either still ongoing at a low level or ended recently enough that the shock hasn't had time to dissipate. The bubbles also appear to be remarkably symmetric about the galactic center. Both the northern and southern bubbles have similar sizes, shapes, and gamma-ray intensities. This symmetry is expected if they were created by a single bipolar event, jets or winds emerging in opposite directions from the galactic center. It would be harder to explain if they were produced by random star formation activity, which would not necessarily produce symmetric structures. But the most tantalizing clue came from observations at other wavelengths. Before the Fermi bubbles were discovered in gamma rays, there were hints of their existence in other data. In 2003, scientists analyzing data from the Wilkinson Microwave Anisotropy Probe, a satellite studying the cosmic microwave background, noticed an anomalous excess of microwave emission near the galactic center. This excess, called the microwave haze, seemed to extend above and below the galactic plane in a pattern similar to what would later be identified as the Fermi bubbles. The haze was interpreted as synchrotron radiation produced by high-energy electrons spiraling around magnetic field lines. If the same electrons were producing both the microwave haze and the gamma-ray emission through inverse Compton scattering, it would provide strong evidence for the leptonic model of the Fermi bubbles. Even earlier, in the 1990s, X-ray observations from the Rosat satellite had revealed structures that might be related to the Fermi bubbles. Soft X-ray emission was detected extending from the galactic center, tracing what appear to be shells or bubbles of hot gas. These X-ray features were smaller than the Fermi bubbles, extending only about half as far from the galactic plane, leading some researchers to propose that the X-ray shells might represent an inner, more recent outburst nested within the larger gamma-ray structures. More recently, observations from the Zeta X-ray telescope, launched in 2019, have revealed even larger structures that encompass the Fermi bubbles. These Zeta bubbles extend even farther from the galactic plane, suggesting a more complex history of outbursts from the galactic center. Perhaps what we see as the Fermi bubbles is just one episode in a long history of activity, with older, more diffuse bubbles stretching even farther into the galactic halo. The connection between these multi-wavelength observations paints a picture of a galactic center that has experienced repeated episodes of violent activity. Each outburst leaves its signature in the surrounding medium. Shells of hot gas detectable in X-rays, populations of relativistic electrons radiating at microwave and gamma-ray wavelengths, and shock fronts that accelerate particles to enormous energies. The Fermi bubbles are not an isolated phenomenon, but part of a larger story of galactic dynamics. Let's zoom out even further and consider what the Fermi bubbles tell us about our galaxy's place in the cosmic ecosystem. Galaxies are not isolated islands. They exist within a vast cosmic web of dark matter and gas, connected by filaments and clustered in groups and clusters. The space between galaxies is not empty, but filled with a diffuse medium called the intergalactic medium, or IGM. Gas flows from the IGM into galaxies, providing fuel for star formation. And gas flows out of galaxies, driven by stellar winds, supernova explosions, and active galactic nuclei, returning enriched material to the IGM. This cycle of gas inflows and outflows is fundamental to galaxy evolution. Without inflows, galaxies would exhaust their gas reservoirs and stop forming stars. Without outflows, galaxies would retain all their gas and potentially form stars too rapidly, burning through their fuel and ending up as dead, red elliptical galaxies. The balance between inflows and outflows, what astronomers call the baryon cycle, regulates the rate at which galaxies form stars over cosmic time. The Fermi bubbles are a dramatic example of outflow. Whatever created them, whether jets from Sagittarius A star, a starburst-driven wind, or both, is pumping energy and material out of the Milky Way's disk and into its halo. Some of this material might eventually fall back onto the disk, enriching it with metals produced by previous generations of stars. Some might escape entirely into intergalactic space, lost forever to our galaxy. By studying the Fermi bubbles, we gain insight into a process that occurs in galaxies throughout the universe. We can observe outflows in other galaxies, but only from the outside. In the Milky Way, we're inside the system, able to study the outflow from within, measuring properties that would be impossible to determine for a distant galaxy. The Fermi bubbles are a cosmic laboratory right in our backyard. Let me take you through what we know about the structure of the bubbles in more detail. The Fermi bubbles extend to galactic latitudes of about 50 degrees above and below the plane, meaning they stretch halfway from the galactic center to the galactic poles as seen from Earth. Given our distance of 26,000 light-years from the galactic center, this corresponds to a physical height of roughly 25,000 light-years for each bubble. The total extent from the top of the northern bubble to the bottom of the southern bubble is about 50,000 light-years. Each bubble has a rough hourglass or figure-8 shape when viewed in projection. They are widest near their midpoints, about 20,000 light-years from the galactic center, and narrower near their bases where they connect to the central region. The edges are remarkably sharp, especially on the east and west sides. The gamma-ray intensity drops off rapidly at the boundary, falling by a factor of 10 or more over a distance of just a few hundred light years. Inside the bubbles, the gamma ray intensity is relatively uniform. There's some substructure visible, including what appear to be jets or streams connecting the base of the bubbles to the galactic center, but overall the emission is remarkably smooth. This uniformity suggests that the cosmic rays responsible for the emission are well mixed throughout the bubble volume, either because they were distributed evenly when the bubbles were inflated or because diffusion has smoothed out any initial variations. The total power radiated by the Fermi bubbles and gamma rays is enormous, roughly 10 to the 37 watts, or about 10 billion times the luminosity of the sun. But this is actually a small fraction of the total energy contained in the bubbles. The gamma rays are just a tracer, produced when a small fraction of the cosmic rays interact with ambient material. The total energy stored in the bubbles, including the kinetic energy of the expanding gas and the energy of the cosmic ray particles, is estimated at about 10 to the 55 to 10 to the 56 ergs. That's roughly equivalent to the energy released by 10,000 to 100,000 supernova explosions. Let's pause on that number for a moment. A single supernova, the explosive death of a massive star, releases about 10 to the 51 ergs of energy. This is more energy than our sun will produce over its entire 10 billion year lifetime. It's enough to outshine an entire galaxy for a few weeks. And the Fermi bubbles contain the equivalent of tens of thousands of supernovae worth of energy. If this energy was released over a relatively short time, say a few million years, the power output would have been staggering. The galactic center would have been a beacon of light and radiation visible across the local group of galaxies. If intelligent beings on a planet orbiting a star in the Andromeda Galaxy had been watching the Milky Way through their telescopes, they would have seen our galaxy flare dramatically, the quiescent spiral suddenly lighting up with the fury of an active galactic nucleus. And then, as the fuel supply was exhausted, the activity would have faded. The jets would have sputtered and died. The accretion disk would have cooled and dissipated. Sagittarius A star would have returned to its slumber, barely sipping at the scraps of gas that drift too close. But the bubbles would remain, slowly expanding into the halo, gradually cooling and fading, a monument to the cataclysm that created them. This is where we find ourselves today. The Fermi bubbles are fossils of a bygone era, cosmic relics of an event that happened before humans existed, before ape ancestors had descended from the trees, before most of the species alive today had evolved. The light that triggers our gamma ray detectors began its journey when mammoths still roamed the Earth, and it carries information about a time when our galaxy was a very different place. But there's another question we should ask. Could it happen again? The answer is almost certainly yes. Sagittarius A star is quiet now, but it won't be quiet forever. The Milky Way is on a collision course with the Andromeda Galaxy, our nearest large galactic neighbor. In about 4 to 5 billion years, the two galaxies will merge, their structures disrupted by gravitational interactions, their gas clouds compressed and funneled toward their respective galactic centers. The result will be a tremendous burst of star formation and, very likely, renewed activity from both supermassive black holes. But we don't need to wait for the Andromeda collision. Smaller events could trigger activity much sooner. Giant molecular clouds occasionally pass near the galactic center. Streams of gas from disrupted dwarf galaxies sometimes find their way to Sagittarius A star. Any significant increase in the fuel supply could wake the sleeping giant and produce new jets, new outbursts, new bubbles. Would such an event be dangerous to life on Earth? Probably not directly. We're far enough from the galactic center that even an active galactic nucleus would pose little immediate threat. The gamma rays from such an outburst would be absorbed by the intervening gas and dust before reaching us. The jets would point perpendicular to the galactic plane, away from our position in the disk. We would be spectators to a cosmic light show, not victims of a cosmic catastrophe. But indirectly, increased activity from the galactic center could have subtle effects. The cosmic ray flux throughout the galaxy might increase, potentially affecting planetary atmospheres and surface radiation levels. The increased ultraviolet and X-ray emission might ionize gas in the disk, affecting star formation rates. Over millions of years, such changes could have noticeable effects on the galactic environment. These are speculations, of course. We don't know exactly when Sagittarius A star will next become active, or how intense that activity might be. What we do know is that the Fermi bubbles prove it has happened before, and there's no reason to think it won't happen again. Let's shift our attention now to some of the more recent discoveries and ongoing research related to the Fermi bubbles. In 2020, the ERO-Zeta telescope aboard the Spectre-RG spacecraft released its first all-sky map in X-ray light. The images were stunning, revealing the hot gas that pervades our galaxy and beyond. But the most dramatic feature was a pair of bubbles, even larger than the Fermi bubbles, extending above and below the galactic plane. These ERO-Zeta bubbles reach heights of roughly 45,000 light-years on each side, nearly twice the extent of the gamma-ray structures. Their edges are more diffuse than the Fermi bubbles, suggesting they represent older, more evolved outflows. The researchers who discovered them proposed that the ERO-Zeta bubbles might be relics of an earlier, more energetic outburst, while the Fermi bubbles represent a more recent event nested within them. This nested bubble interpretation suggests that the galactic center has experienced multiple episodes of activity over tens of millions of years. Each outburst inflates a new set of bubbles, which then expand and cool while subsequent outbursts create smaller, hotter structures inside. The X-ray and gamma-ray bubbles would thus represent a timeline of galactic center activity, with the oldest events traced by the most extended structures and the most recent events traced by the sharpest, most energetic features. There's even some evidence for this hierarchy within the Fermi bubbles themselves. High-resolution gamma-ray observations have revealed what appears to be a jet-like feature extending from the galactic center into the base of the southern bubble. This feature, sometimes called the cocoon or the jet, might represent ongoing activity or a very recent outburst embedded within the larger bubble structure. If confirmed, it would suggest that the galactic center is not completely dormant, but experiences occasional hiccups of activity even today. The polarization of light from the Fermi bubbles has also provided important insights. When high-energy electrons spiral around magnetic field lines, they emit polarized radiation, light whose electric field oscillates in a preferred direction. By measuring this polarization, astronomers can map the magnetic field structure within the bubbles. Observations from the Planck satellite and ground-based radio telescopes have revealed that the bubbles contain ordered magnetic fields. Near the edges of the bubbles, the magnetic field appears to run parallel to the boundary, suggesting that the field has been compressed and aligned by the expanding shock front. Inside the bubbles, the field is more complex, with indications of helical or tangled structures that might result from the interaction between the inflating jets and the ambient medium. These magnetic fields play a crucial role in confining the cosmic rays within the bubbles. Without magnetic confinement, the high-energy particles would quickly escape into the surrounding halo, and the gamma-ray emission would fade. The fact that the Fermi bubbles remain bright millions of years after their creation suggests that their magnetic fields are effectively trapping the cosmic ray population, allowing the particles to bounce back and forth within the bubble volume, continuously interacting with ambient photons and gas to produce gamma rays. Let's talk about what the future holds for research on the Fermi bubbles. The Fermi telescope continues to operate, accumulating more data and refining our view of the gamma-ray sky. With each passing year, the statistical significance of the bubble detection improves, allowing scientists to look for fainter substructures and to better constrain the spectral properties of the emission. Future generations of gamma-ray telescopes, such as the proposed All-Sky Medium Energy Gamma Ray Observatory, AMEGO, or the Cherenkov Telescope Array, CTA, will provide even more detailed views of the Fermi bubbles, potentially resolving individual features and tracking the emission to higher energies. At other wavelengths, ongoing surveys are providing complementary information. Radio telescopes are mapping the synchrotron emission from relativistic electrons, revealing the magnetic field structure and the distribution of cosmic ray electrons. X-ray observatories are tracing the hot gas, constraining the temperature and density of the plasma within and surrounding the bubbles. Optical and infrared telescopes are observing the absorption signatures of gas in front of background sources, providing information about the velocity and composition of material in the bubbles. One particularly exciting avenue of research involves neutrino telescopes. When cosmic ray protons collide with ambient material, they produce not only gamma rays but also neutrinos, ghostly particles that pass through matter almost without interacting. If the Fermi bubbles are significant sources of hadronic gamma rays, they should also be sources of high-energy neutrinos. Neutrino telescopes like IceCube in Antarctica are searching for these signals, and a detection would provide definitive evidence for cosmic ray protons in the bubbles, helping to resolve the debate over the origin of the gamma-ray emission. The broader implications of the Fermi bubbles for our understanding of galaxy evolution continue to drive research. Simulations of galactic outflows are becoming increasingly sophisticated, incorporating realistic physics for jet launching, cosmic ray transport, and interaction with the surrounding medium. By comparing these simulations with observations of the Fermi bubbles, scientists can test their models and improve their understanding of how feedback from galactic nuclei shapes their host galaxies over cosmic time. The Fermi bubbles are also a reminder of the dynamic, ever-changing nature of our universe. On human timescales, the night sky appears constant. The same stars shine down on us that shone on our ancestors thousands of years ago. The constellations hold their shapes. The Milky Way stretches across the heavens, and the cosmos seems eternal and unchanging. But this perception is an illusion born of our brief existence. On cosmic timescales, everything changes. Stars are born and die. Galaxies collide and merge. Supermassive black holes feast and slumber. The Milky Way we see today is not the Milky Way of 10 million years ago, and it will not be the Milky Way of 10 million years hence. The Fermi bubbles are a window into this dynamism, a reminder that our seemingly peaceful galaxy has a violent past and an uncertain future. When we look up at the night sky and trace the band of the Milky Way from horizon to horizon, we're looking at the disk of our galaxy edge-on. We can see the accumulated light of hundreds of billions of stars, the dark lanes where dust absorbs the background glow, the bright concentrations where star formation is most intense. But we cannot see the bubbles. They are invisible to our eyes, radiating their gamma-ray glow in a part of the spectrum we cannot perceive without instruments. And yet they are there, 25,000 light-years above our heads and 25,000 light-years below our feet, assuming we define up and down relative to the galactic plane. Vast structures of superheated gas and relativistic particles, inflated by an ancient cataclysm, slowly expanding into the void. They are a testament to the violent forces that shape galaxies. They are a clue to the activity of the monster that lurks at the heart of the Milky Way. They are one of the most remarkable discoveries of modern astronomy. The story of the Fermi Bubbles is far from complete. Each new observation raises new questions. Each answered mystery reveals deeper puzzles. We are still in the early stages of understanding these structures, still gathering the data and developing the theories that will eventually explain their origin and evolution. Decades from now, astronomers will look back on this era as the beginning of a new understanding of galactic dynamics. And perhaps someday, we will witness the next great outburst. Perhaps in a few million years, or a few 100 million years, Sagittarius A star will awaken again. Fresh jets will lance out from the galactic center. New bubbles will begin to inflate, their shock fronts accelerating particles to extraordinary energies. The cycle will begin anew. When that happens, if there are still beings on Earth capable of looking up and wondering, they will see what we cannot. A galaxy in the throes of transformation, a cosmic cataclysm unfolding in real time. The Fermi bubbles we study today will have long since faded, replaced by new structures, new mysteries, new questions to answer. But for now, we are privileged to witness the aftermath of one such event. We live in a galaxy with scars, a galaxy with a history written in gamma rays. And by reading that history, we learn not just about the Milky Way, but about the processes that shape galaxies throughout the universe. This is why we study the Fermi bubbles, not merely out of curiosity, though curiosity is reason enough. Not merely because they are beautiful, though they are beautiful in ways that transcend our visual perception. We study them because they teach us about our cosmic home, about the forces that have shaped it, and about the future that awaits it. We study them because in understanding them, we understand ourselves a little better, our place in a vast and dynamic universe, our connection to events that happened before we existed, our role as witnesses to the cosmic drama unfolding around us. The Fermi bubbles may be invisible to our eyes, but they are not invisible to our instruments, our minds, or our imagination. Through the careful work of scientists around the world, these hidden giants are revealing their secrets, one gamma ray at a time. And that is a story worth telling.